We're now going to go back to chapters 17 and 18 and talk a little bit about probability. So you might remember in those particular chapters you learned about what probability is, what this idea of randomness is all about. We talked about probability models and how to use those models to answer certain kinds of questions. We also talked about what makes a legitimate probability model. So let's review that a little bit. So here's a particular scenario. A psychologist thinks that listening to Bach helps people think. She gives subjects a set of puzzles and measures how many they solve in 5 minutes while listening to Bach. From data on many people, the psychologist gets this probability model. So remember what a probability model is. It's telling us all the possible outcomes of a random phenomenon and the probabilities associated with each of those different outcomes. So here we see that the total number of puzzles solved can be 5, and we're seeing the probabilities associated with solving a certain number of puzzles while listening to Bach. So we could present you with a model like this, and we want you to look carefully at this model. So think about this idea of what probability is, what kind of values a probability can take on, what makes a legitimate probability model. So do you think this particular model is legitimate? And how do you know? You might remember when we were talking about chapters 17 and 18, we talked about 2 things that you really want to focus on and look at to determine if a probability model is legitimate. First of all, you want to look at those individual probabilities, and you want to make sure that each one is no less than 0 and no greater than 1. So remember, probabilities are numbers that are generally between 0 and 1. They can't be more than 1 or less than 0. And obviously here we're seeing that. So we see nothing that's less than 0, so nothing that's negative. We see nothing that's greater than 1. So we know we have that condition met. A second condition, remember, is that if the model is legitimate, then if you add together all the probabilities of all the different outcomes, the sum of all those probabilities will be 1. So if you add these numbers together, again, just add all of these numbers together, you will see that the sum is 1. So we get, and I'll just quickly show you this in case it's not making sense verbally. But I just want to add all these together. And again, that's going to come out to 1. So if we ask you if something is legitimate, we want you to look at those 2 things. Look at the individual probabilities, look at the sum of all the probabilities. Okay, so let me just correct my writing a little bit here. Here's another question we might ask you. So do you think this is true or false? The probability that at least 3 puzzles are solved in 5 minutes is 0.3. So as you're looking at this probability model, what do you think? So here's 3, and we do see 0.3. So if the question had been the probability that exactly 3 puzzles are solved in 5 minutes is 0.3, then this would be a true statement. At least 3. So what does at least 3 mean? I'm hoping you're remembering that at least 3 would have to mean 3 or more. So at least 3 means 3 or more. If we said at most 3, that would mean 3 or less. So at least 3, to figure out that probability, you would have to add together the probability of solving 3 puzzles, or 4 puzzles, or 5 puzzles. So that would actually give us 0.5. So this statement is false. So think about what it means if we say at least or at most. You might see those terms a lot in different kinds of problems, and we want you to know that at least means that that particular number is the lowest possible outcome. At most would mean that particular number would be the highest possible outcome. And generally then you're going to have to add together one or a couple, I'm sorry, I'm not making sense, but generally, if you're asked something like at least 3, you're going to have to add together 3 and some other things, whatever's above 3. So at most 3, you'd have to take the probability of 3 and add whatever's lower than that. So I hope that's making sense. We just, again, want you to kind of have this understanding of at least and at most, and how those are different things, and would require you to be looking at different aspects of your data or at your probability model. So what are some other things that we might ask you about probability? Here are some true or false questions. So think about what you would answer here. Again, you might look at these slides, write down your answers, come back, see if you got the right answer. When you flip a thumbtack into the air, or in the air, it can land point up or point down. Since there are just two possibilities, the chance of each one must be 50%. So I'm hoping that you're saying false. And again, I'm hoping that you're thinking back to some things that we talked about in chapter 17 about how, sometimes you might have two outcomes and they're each going to be equally likely, like tossing a coin. If the coin is weighted properly, fairly, we wouldn't expect heads to come up more than tails. We'd expect each side to have an equal chance of coming up. Other things, however, even though there might just be two possible outcomes, that doesn't mean that each outcome is equally likely to occur. In an emergency room, if an emergency room sees 12 patients in a row with heart attacks, then it becomes more likely that the next patient will have a different problem. Again, I'm hoping you're saying false. And why? So we talked a little bit about this idea of the myth of the law of averages, that if we see lots of particular outcomes in a row, that sometimes tricks us into thinking that what's going to happen next is more or less likely based on what happened before that. So even if you see 12 in a row of one thing, that doesn't make something else more or less likely to happen. Each particular outcome is independent of every other outcome, does not affect every other outcome. Probabilities can be less than 0. So we just talked about this. I'm hoping you're remembering that that's false. Correlations can be less than 0. Okay, that's true. So correlations can be negative or positive. So just having this understanding, we've talked about a lot of different things so far this semester. Values that sometimes can be negative, sometimes cannot be negative. So really remembering that and thinking about that. What can be negative? Are there certain things that can only take on particular values, like probabilities or correlations? How does this compare to something like a z-score, which can be negative or positive and can take on lots of different values? With a z-score, for example, you're not restricted to values between -1 and +1 as you would be with a correlation. Okay. Let's now look at a new example here. So, and now we're starting to review correlation and regression. So that was our last topic this semester. Hopefully it's still pretty fresh in your minds. Members of a football team were asked to do as many push-ups as they could in 2 minutes. The scatter plot below shows how the number of push-ups relates to the weight in pounds of the football players. Okay, so here is what we're seeing. So weight, notice, is along the x-axis, and number of push-ups is along the y-axis. So this is a scatter plot. Again, we use a scatter plot when we want to look at the relationship between two quantitative variables. Each of these statements, let me know if you think they're true or false. And I want you to judge this based on what you're seeing in the scatter plot and what you know about this particular scenario. The heaviest players tend to do more push-ups in 2 minutes than the lighter players. Okay, so if that were the case, as weight goes up, number of push-ups goes up, that would signal that we would need to have a positive relationship between the variables. And I'm hoping you're seeing that this is a negative relationship. So that would be a false statement. Here, the heaviest players tend to do the least number of push-ups. So as weight goes up, push-ups goes down. If the players' weights were converted to kilograms, the correlation would get weaker. So if we're changing the units for one of our variables, how would that change the correlation? Again, I'm hoping you're saying false. I'm hoping you're remembering what we talked about correlation, how it's not affected by units, how we could change our units and that's not going to change what the correlation is. As long as we're still measuring the same things and looking at the same relationship or the same two variables, changing units from something like pounds to kilograms is not going to change what the correlation ends up being. If we instead plotted weight on the y-axis and number of push-ups on the x-axis, the correlation would remain the same. So if we switched our variables here, would that make a difference in terms of what the correlation would be? The correlation would be the same. So the correlation doesn't care what's on the x-axis or what's on the y-axis. The correlation would be the same. What would change if you switch the axes would be the slope and the intercept. So if you're figuring out a regression equation, it does matter what's on the y and the x-axis. So that'll have an impact on those values in the equation. So I'm not sure if you can see this clearly. Let me pull this down a little bit. But the final question here is, the graph shows a strong negative association between weight and push-ups. I would say that part of that's correct. There's definitely a negative association, but I would not call it a strong association. I would say it's more moderate, maybe even tending to be on the weaker side of moderate. So there's obviously something going on here, but it's clearly not a strong relationship. And remember, we judge strength by thinking of where that line would be in the plot and how the points are clustered around the line. If they're pretty close to the line, that's a stronger relationship. As they get further away from the line, that's a weaker relationship. Okay, let's try to go through a few other things and then we'll wrap up this particular video. Let's say I'm interested in predicting the weight in pounds of a pumpkin based on the number of seeds in the pumpkin. So this is based on a true story of actual data that was collected. The scatter plot below shows the relationship between weight and number of seeds for a random sample of pumpkins. The correlation between these variables is R equals 0.69. So based on this, which of the following statements is false? 69, and actually let me just maybe show you all of them and we'll go through each one. So looking at these particular statements here, 69% of the variability in weight can be explained by the number of seeds. So you might remember learning about something that tells us the percentage of the variability in the response that can be explained by the regression equation or by the explanatory variable. So if I'm getting 69% here, hopefully you can see that what I essentially am doing is I'm taking this and I'm just multiplying it by 100. So can we do that? Can we take a correlation, multiply it by 100%, and make a statement like this? So think about that. We'll come back to that in a minute. The slope of the regression line is positive. I would say that's true. So we can see positive relationship here. So that's a true statement. It is appropriate to predict the weight of a pumpkin that has 597 seeds. So where would 597 be? It's going to be over here somewhere. So yes, this is appropriate. So remember, we can use the equation as long as those variables or those values of x are within the values that were used to create that regression line, to create that equation. It is not appropriate to predict the weight of a pumpkin that has 1,200 seeds. So where would 1,200 be? That would be out here. So if we try to use the equation to predict this, we would be engaging in something called extrapolation. And remember, that is a bad thing. We don't want to be extrapolating. So obviously D is correct. We would not want to use the equation with this particular variable, but it's okay to use the equation with this particular variable. So C would not be extrapolation. So I pretty much ruled out B, C, and D. So even if you weren't totally convinced maybe that A was the correct answer here, think about trying to rule out other possible answers. So sometimes that can help you work backward to get at the correct answer. But my hope is that you're having this understanding of what it means to say we have a certain percentage of variability in the response that can be explained by the equation, or that can be explained by that x value, that explanatory value. Hopefully you're remembering that to get that number, you have to take r and you have to square it. So that the value would not actually be 69%, but we'd have to square this number and then multiply it by 100%. to get what that answer should be. And we'll come back in a little bit and actually talk about what that answer ends up being and how we can interpret that in other ways. So I'm going to pause here and we'll come back and try to wrap things up as quickly as we can.